The celestial sphere makes a complete revolution around the Earth in 23 hours, 56 minutes and 4 seconds. In Silent Hunter 5 world, this is not always the case. Changing the time compression modes during the game violates the regularity of the movement of celestial bodies in time. Silent Hunter 5 chronometer readings become irrelevant for celestial navigation. Silent Hunter 5 new sextant modification from Subsim by Yellow Submarine completely solves this problem. The file description contains a warning that it is only compatible with TWOS 2.2.9 and 2.2.10 version. I have tested this sextant modification with TWOS version 2.2.22. In some cases, attempts to start the game led to the closure of the game with ejection to the desktop. But as a rule, from the second or at least the third time I was able to start the game. The game itself is stable and I didn't have any ejections to the desktop during the game. Subsim forum reported that this sextant modification could make it difficult to transition to the new campaign. During the game I made the transition to the new campaign without any problems, following the standard guidelines outlined in the TWOS 2.2.22 documentation. At the end of this video, I will show how I determine the U-boat position using this sextant modification along with TWOS 2.2.22 version. New sextant modification makes significant changes to how sextant works. First, the sextant corrects the time and displays the corrected time. Second, the sextant simulates atmospheric refraction and other factors that require corrections to the measured altitude. Third, the display of the sextant now has no azimuth. In reality, azimuth is not measured with a sextant but calculated from tables. The new sextant has one drawback. It performs a time correction using the historical coordinates of celestial bodies that took place in reality. Since the coordinates of the celestial bodies in Silent Hunter 5 world do not fully correspond to the historical coordinates, I made the necessary corrections for 21 stars. There is still more work to be done to correct the declination of the sun, but you can already use the sextant for accurate celestial navigation with 24 stars. After downloading sextant modification, you need to unpack the contents of the archive in the TWOS parts folder. Follow the links in the video description to download the fixes for the stars and replace the corresponding files in sextant modification. Next, use the generic mod enabler to activate sextant modification. In this tutorial we'll learn how to determine the U-boat position by 2 stars. From the previous lessons you know what zenith distance is. In celestial navigation we use the fact that the zenith distance corresponds to the distance from the U-boat position to the projection of a celestial body onto the Earth's surface. So, being on the surface of the Earth and having measured the altitude of the star, you know the zenith distance. This is not enough to determine the U-boat position, but we can plot navigational isoline. I talked about navigational isolines in more detail in the first lesson. Navigational isoline in this case is a circle which is a collection of all points on the surface of the Earth, relative to which this star has a given zenith distance at a particular moment in time. In other words, this is the set of all points at which you can probably be if you don't know anything other than the zenith distance. If you observe two stars from one point, then you can plot the second navigational isolines. Thus, out of the whole set of points, there are only 2 points at which you can be and simultaneously observe these two stars. These are the intersection points of 2 navigational isolines. You do not need to determine which of these 2 points you are in. Your task is to clarify how much your actual position is shifted relative to the dead reckoning position. Dead reckoning position is your calculated position based on the fact that you moved from a point with the known coordinates in a given direction at certain speed for a certain time. If you are not sure about the calculation of your position as a dead reckoning position, you can choose a point based not on the calculation but on the basis of your assumption regarding your position. In practice, celestial navigation is a fixing of dead reckoning position by the method of transverse. The positions of the navigational isolines correspond to the azimuths of the observed stars. In previous tutorials, we made a distinction between azimuth and true azimuth, as they were used in the sextant interface. Now, hereinafter, we will use only the concept of azimuth, implying the angle between the direction to the north and the direction to the celestial body. Isolines are actually circles, but in practice, celestial navigation proceeds from the fact that navigational isolines have a very large radius, and on maps with a large scale, their curvature can be disregarded. Navigational isolines are depicted as straight lines called lines of positions. A line of position forms a right angle with the azimuth to which it corresponds. It is not difficult to understand how method of transverse works. SH5 world is as flat as a chessboard, but this does not make it difficult for celestial navigation. In SH5, celestial bodies change their position just as if you were on a spherical surface of the Earth. Imagine that this is the visible part of the celestial sphere. The zenith is marked with a green mark. A red mark is dead reckoning position. We do not know our exact location, but we assume that we are at the red mark and set the celestial sphere so that the zenith is exactly above the red mark. We measure the altitude of the star with a sextant. The image of the star will be applied to the celestial sphere with a black marker, according to the measured altitude at the place of our actual location. This direction corresponds to the star's azimuth. The line at right angles to the azimuth is line of position. Using the formula, we calculate the altitude of the star, which should take place if we were actually in the dead reckoning position. The calculation formula involves latitude of dead reckoning position, declination of the observed star, and local hour angle. What is local hour angle and how it is calculated was discussed in detail in the previous video. Let's say the calculated altitude is less than measured altitude by some amount. We will show in red color on the celestial sphere the position of the observed star in accordance with the calculated altitude. This tells us that the actual U-boat position is offset in azimuth from the dead reckoning position by an amount that corresponds to the difference between the measured altitude and the calculated altitude. If we transfer the U-boat position in the azimuth direction by a distance that corresponds to this difference, that the calculated altitude will coincide with the measured altitude. To show this on the map, we must make to the appropriate transfer of the line of position. The line of position property is that the U-boat position can be located at any point that lies on the line of position within a radius of many tens of kilometers. Being at any of the points on this line at a given moment in time, you will observe practically the same altitude and azimuth of the observed star. Due to the small size of the celestial sphere layout, it may seem to you that moving along the line of position, the altitude and azimuth of the stars should change significantly, but we must understand that celestial bodies are located far enough, and the basic concept of astronomy is that the size of the celestial sphere is comparison with the size of the Earth is taken to be infinitely large. Thus, displacement of the U-boat position along the line of position by many tens of kilometers will not lead to a significant change in altitude and azimuth. To find out exactly at what point on this line the U-boat is, you must have at least one more line of position that will intersect this line of position. For each of two stars, we calculate the transfer of the line of position. If the result is positive, you must make a transfer in the direction of the azimuth. If the result is negative, then the transfer is performed in the direction opposite the azimuth. On the SH5 map, 1 minute of arc corresponds to 2 kilometers. Transfer, which we have calculated in arc minutes, must be divided by 2 to get transfer value in kilometers and plot it on the map. When transferring position lines, it is necessary to maintain a right angle with respect to the corresponding azimuths. As a result, we get the point of intersection, the position lines. If we made drawings directly on the spherical surface of the Earth, then this point would correspond to the U-boat position. But we are working with a map. A map is a way to represent a spherical surface on the plane. The transferring an image from a sphere to a plane, distortions occur. A specific way to represent the Earth's surface on a map is map projection. SH5 map projection does not distort geographic meridians. All proportions are maintained in the north-south direction. At the same time, the image is stretched along the geographic parallels. The farther from the equator, the more the image is stretched in west-east direction. The stretch ratio can be calculated in a case-by-case basis. For celestial navigation, this must be done before plotting observed position on the map. On the map SH5, you can see that all parallels are stretched to the length of the equator. To calculate the degree of stretch of a parallel, you need to solve a right-angled triangle. The cosine of latitude is the conversion factor from the parallel length to the equatorial length. Remember this. Look at the yellow line segment. This is the difference between the longitude of the dead reckoning position and your position without considering the parallel stretching on the map. I call this line segment by spherical transfer, meaning that our position would be at this point if we were drawing on a spherical surface. To plot our position on the map, we need to divide the length of this line segment by the cosine of latitude. You can practice celestial navigation by doing the drawing exercises on the map. In order not to waste time on long calculation, you can use my Excel spreadsheet. You can download this table and other necessary tables for celestial navigation from the links in the description. I'll show you how to use it.
Schiff in Sicht, Kurs frei.
Each navigational star is assigned a number. Before measuring, you must enter the number of the star you will be measuring. The new sextant automatically adjusts the time to the measured altitude of the star. The measured altitude, universal time, and date must be recorded. It is necessary to enter the initial data for the calculation into the calculation table.
Äußerste Fahrt voraus, kleine Fahrt voraus.
If you took measurements on the surface, indicate the depth of 5 meters in the table. Next, enter latitude and longitude of dead reckoning position. Enter universal time and date according to universal time. Enter the Greenwich hour angle of Aries value into the table for the specified date and time from SH5 almanac. Enter the observed altitude of the star. Take from the table azimuth and value of the transfer in the azimuth direction for both stars. Plot the transfers on the map. This is a spherical transfer. Not necessary to use a formula to find the map transfer. You can solve this problem graphically with the right-angled triangle. Plot the U-boat position on the map.